Partitioning or database partitioning is a technique where you split up a huge table into multiple tables and let the database decide which table or which partition to hit based on the where clause. It is a very, very genius design, and I'm going to discuss it in this video. How about we jump into it, guys? So here's what we're going to discuss in this particular video, guys. So what is partitioning? Why does it exist? Because that's the question we always ask. Why does any technology exist? All right, so we're going to ask what is partitioning. We're going to answer that. We're going to talk about horizontal partitioning and vertical partitioning, guys. So that's a very, very critical concept, right? What is the difference between them? And from now on, whenever I say partitioning, I'm always referring to horizontal partitioning, and that's people rarely use vertical partitioning these days. It's like normalization, almost like vertical partitioning. Partitioning types, what kind of types of partitioning we have, what can we do to do partitioning, different kind of partitioning. And then we're going to describe partitioning versus sharding, which is another video I discussed. It's specific to sharding, right? A little bit more complex than partitioning, right? We're going to explain the difference between the two. We're going to do a demo because that's the beautiful thing. Going to use Postgres to do a demo to show you a table with 10 million rows and how to partition that stuff. I'm going to discuss finally the pros and cons and then summarize the whole thing. All right, so what is partitioning, guys? So let's say we have a beautiful customer table here. This is like, I don't know, 1 million row of table. 1 million is not that big, guys, by the way. But if I want to pick the name of a customer with this particular ID, 701, right? So you're going to do select name from customer tables where ID equals 700,001. So what the database will do is, well, if you have an index on that table, we're gonna use the index and then we're gonna land on that particular row on the disk, right? Or if we don't have it, we're gonna do a sequential scan, which is that's the worst thing we can do, but we have to scan all these rows until we find the rows we're looking for. Regardless whether you're using an index or sequential scan, scanning a million row is a lot, right? And multiply that by 10 or 1,000 billion rows. That's going to slow things down. Index, large tables are always slow to query, regardless, right? So what do we do? Partitioning is the idea here is break the table down into smaller pieces so we know we all only work with so many rows instead of larger set of rows. So that's the one idea. Let's break out this 1 million rows into 5 partitions, 5 tables. Partitions is nothing but a table. And we're going to name them customers 200K, customers 400K, customers 600K, customers 800K, and customers 1 million. So that means basically these are the customers between 1 and 200. These are the customers between 201 and 400, customers between 401 and 600, and so on. You get the idea, right? So that's just how we partitioned it. And then the database, magically, you're going to attach these partitions to the main table, which is customers table. So customers table is just almost like a parent or inheritance. It doesn't have any data. That actual data exists on these table. So now what I do is I'm going to do the same exact query. Select name from customers table where ID equals 701. And the first question is, I'm going to send that query. What do we do? Where does this ID exist? And that's a very quick check by the database. It's like 701. Which table should I query? This, or this? It's very easy because which partition is customer 701 in? We have the definitions in this partition. There is metadata attached with it. Where 700 is between 800 and 1 million, which is 600 and 800. So that's exactly the table we need to query. So partition customers 800K, we hit that table immediately. So now I'm working only with 200,000 rows, which is beautiful. I always say, I tweet that the other day, the quickest way to query a table with 1 billion rows is to avoid querying a table with 1 billion rows. And that's what the database do. They just try to, as much as possible, to avoid querying this much data and work with a smaller set of data. That's the trick here. All right, so now once I have this, if I have an index, even better, right? I'm going to use the index and then land on customer 700,001, which is Kim in this case. Beautiful. So that's partitioning. So let's discuss vertical versus horizontal partitioning. Horizontal partitioning is splitting the partitions by rows, as we discussed in this case, right? Customers from this rows to this ID to this ID is in this partition. Another customers from this ID to this ID is this partition. So we're splitting by rows, like almost like horizontally. Just imagine this is like a knife, right? It's just like slicing in the middle. You're slicing the table in the middle, and then breaking the partitions into multiple ones, right? So that's the partition. And there's like types of partition, like by ranges, like we did, or by list, like zip code. Or 90205 is on this table. Partition zip code 91111 is on this table, right? So by list or by range. Vertical partition, on the other hand, is you splitting literally vertically from top to bottom. And what you do is essentially you split columns within is entire chunk of rows into a complete different partition, right? This is useful for, like, let's say you have a large column that is a blob and you barely query that blob document, right? You don't want that blob token to take from your precious SSD space or the fast access, right, that you have. So we're gonna vertically partition it, put it in another table space, put it in its own table with its all documents, and then attach it to your master table. But if you query for that, the database knows, oh, this particular column is in another table, so I have to jump into that particular table to pull it. However, my beautiful fast access columns are in a fast access, in a proper table space, in a proper SSD drive, and they are compact. They are not as large. So I just saved a lot of space in my disk. I just saved also a lot of access speed too. So vertical partitioning. Partitioning type. So that's what we did. Partitioning range. That's the example I gave. IDs. You can partition by log date. Let's say you have an IoT device that's spitting out measurement or something like that, and there's a log date with every single measurement, and you go on a partition like, oh, 2012 data, 2013 data, 2020 data on each year by partition, or each quarter or each month, put it in a given partition. So that's range, right? From this date to this date, throw it in this partition. And then the beauty of this, like, oh, this table, this partition is old and nobody uses it anymore. Who's gonna query 1995 data anymore? So let's move it into a slower archive that's, like, I don't know, running on tape somewhere. So if it's slow, I don't care. So that's range. By list, discrete values. States, for example, California, all rows or any customer in California goes in this table. This is not range. This is a value. So hey, that partition is for California people. That partition is for Alabama. Or zip codes, right? Or countries, the same thing, right? So that's by list. That's another way of partitioning. By hash, another popular thing, especially Cassandra uses that, right? Where it uses a hash function to spread the value. So hash function that gives you a hash. If you got this hash, go to this table. If you get this hash, go to this table. So it's a very, very popular thing. I know in the proxies we use IP hash to kind of decide which backend to hit based on the IP. So that's another idea. Horizontal partitioning, or just partitioning versus sharding. So guys, we made a video about sharding. Partitioning versus sharding is very interesting, and let's discuss the difference between the two. Horizontal partitioning, or just partitioning, splits the big table into multiple tables in the same database, and the database takes care of the management of these partitions. You as a client, as a query builder, you have no idea what partition you're hitting. The database is deciding. So that's why I said the client is agnostic. It doesn't care which partition it's going to hit. The database, I'm sending my own beautiful query, and the database decides which partition to hit based on the logic on the where clause, right? So that's the trick here. Sharding, on the other hand, splits the big table into also multiple tables. However, they are completely different servers. They are on completely different database servers. And you do this for distributed essentially processing, right? It's like, hey, let's throw this into different tables, right, altogether, in different servers altogether. So that, like, basically for latency issues, like I say, California customers, we're gonna put a database shard just for California customers, and you're gonna hit, if you're from California, we're gonna hit you based on a like a proxy SQL. We're gonna detect where IP address we're from, and we're gonna serve you to the database, or if it's a read, for example, to the database instance that has the California table, right? Versus if you're going from Asia, we're gonna hit you with an Asian server, right? So that's you hit that IP address. It's different, completely different IP address. So that's a beautiful, beautiful design. Obviously, it's a little bit complicated, but yeah. So if you think about it, the client is aware of the shard, right? Which is a big no-no in sharding. That's one of the big things that I don't like about sharding. I know Vitas and other technologies are trying to solve this, but still, it's a big investment for anyone as back-end engineers. So the table names, this is like a little bit of a just detail. The horizontal partitioning table name changes, right? Of that back end, you have like multiple table names and they are changed, right? However, in the sharding case, this table name stays the same almost, right? Because the query is exactly identical, doesn't change, right? But the server to which you're executing the query against actually changes. Demo, let's jump into this, guy. So what we're gonna do here, guys, we're gonna use Docker. We're gonna spin up a beautiful Postgres instance, and then we're gonna insert around 10 million rows in that table, and then we're gonna create table partitions, and then we're gonna join the partitions to the master table, and then do some fancy queries, explain, and all that jazz, right? How about we jump into it, guys? All right, guys, let's just jump into the demo, guys. So requirement here, just have Docker, and that's it. Because I'm gonna spin up a Postgres instance, because I play with this. It's way easier than installing Postgres on my own machine. But if you have it, never mind. So once you have that, I'm gonna actually run a Docker command here, right? And I don't need to expose the port for Postgres, because I'm gonna bash into the container inside Postgres, and I'm gonna run the SQL commands inside Postgres container. So I'm gonna do Docker run, and then all I have to do is like basically do -- name, give it a name. Let's call it pg main whatever, right? That's the name of the container. And then once I have that, I want to detach this container, right? Because I want to use the same terminal. And then finally do an environment variable, Postgres password. That's a requirement, recent one. Just give it a Postgres password, any password. And then finally just do Postgres. This is the image we're gonna pull from. And then just like that, we spun up a Postgres instance. If I do docker ps, we can have that. We have a Postgres instance running, and this is my name. So now what we're gonna do is go docker execute interactive terminal. I wanna jump into pg main. Inside it, right, I wanna run the command bash, right? And then once we bash into the container, I want to do psql-u, which is the username, and Postgres. And just like that, since I am the owner of this, it's going to let me in immediately. So now I'm in the beautiful Postgres command, right? And I can do stuff, right? All right. So here's what I'm going to do. I'm going to create a table, guys. I'm gonna call this create table grades. This is just a bunch of student grades, and I'm not gonna maintain names of the students or anything. This is just a garbage table where we have literally an ID, a sequence ID that just 1, 2, 3, 4, 5, 6, and a grade. That's it, right? Nothing else. So I'm gonna call it grades original, right? And then I am going to give it an ID. Serial, that means every row I insert will automatically get a sequence and increment. I'm going to make it not null. This is a requirement for partitioning. Everything should be not null, right? Everything that you're partitioned against should be not null. And then I'm going to do a G, which is the grade itself, G. And that's also an integer, not null. And just like that, we're ready. So now I'm going to insert around 10 million rows in this table, and that's extremely easy to do. So all we have to do is insert into grades original. I'm going to insert it before I add an index to the G, just because it's faster this way, right? Because I don't have to maintain the index while I'm inserting this stuff. So I'm going to insert this, select star, not star, select, here's what I'm going to do. I'm going to floor a random function which the random function gives me fractions like 0.09, 0.0 to 0.09. That's the maximum number. So I'm going to multiply the random by 100. That gives me values from 0 to 99. And that's exactly the grades, right? Out of 100, essentially. Not quite 100. I'm not going to get 100, but who cares, right? So and then I'm going to floor the whole thing because I'm going to get the fraction. The floor will give me the function. So now selecting this from generate series, this is a function that you basically will, every time you call it, you specify how many times you want to call it. And I want to call it 10 million times. And I just added this comment so I can see for myself. So it's actually like that. And then let's just insert and let's just wait. Oh, bad. Okay. So what I'm going to do, I forgot to specify the column. So insert into, so I have to do G. I guess I didn't specify the field itself. That's my bad. So what will happen here is the ID you don't have to specify because it will be auto-generated. But the G, you have to specify it and the value will go to the G. These values, and just like that we have a 10 million rows. Obviously we can generate more, but this is just for example's sake. Nice. So now let's create an index on that. Create index, let's call it grades original index on grades, what do we call it? Grades original org on G. That's it. So this will create an index, so that create a beautiful index. And we talked about indexing, guys. And that's it. We have an index. So let's describe the table we have here. Boom. Just like that. We have an ID. We have a G. Nice. So now if I do select count star from grades original, where G is equal 30, right? How many rows? We have around 10,000 rows that are called 30. And then let's do this fancy thing in Sports. It's called explain analyze, which will explain how they came up with this result, and it will tell you how long it took. So it took 2 seconds to execute this query, 2000 millisecond, and it took like a 0.97 millisecond to plan it. And we used bitmap index scan. That means we handpicked the values from the index and we went to the table, right? Sometimes this works, sometimes this actually comes slow, right? And this is the number of rows that came back. So now if I do where G between 30 and let's say 35, that's a kind of different query, right? It's a range query. So it's gonna be a little bit slower. And as we see, it's like it took 3 seconds to execute. And still, the database decided to do with parallel index scan this time, and then jumped back to the index and calculated the values. So that's what we see here, guys. So how about we do partitioning? To do partitioning, guys, we're gonna create the main table, right? Which is called table. Let's call it grades parts, right? And here's the trick, guys. It's the same thing. Serial, not null, and then the grade integer, not null also, but you have to say partition by range. And which is the range in this case? The G will be the ranged here, right? We didn't define the range, but you have to create this table with partition in mind. And just like that, we created it. Now, you're responsible to create all the ranges, all the partition yourself. The database is not going to do this for you. So I'm going to create the partition one by one now. And I'm going to define the partition as G, which is just like the name of the table, and then 0, 35. So grades from 0 to 35 goes into this table. How do I do that? Create table G00, and I'm going to make this exactly like the table above that, right? So like the grades parts table. And I'm going to include indexes. I don't have to do that because there are no indexes in this table, remember? What I'm going to do is I'm going to add the indexes after the fact. It's okay. So now we have G035. It's just a normal table for now. I just want to copy the same exact structure. So if I describe this table, we have ID and G, and there's no indexes or anything. So let's go ahead and create the rest of the tables. From 35 to 60, let's say. And then we're going to create from 60 to 80, and then finally from 80 to 100. These are the four partitions in this case, only four partitions. And now what I'm going to do, I am going to attach the partitions on my main one by one to my major table, right? And to do that, I do alter table. Which table? Of course, the grades parts. That's the partition table, right? Attach partition G0035, which is this table, for values. Which values are this allowed for this table? For values from 0 to 35. That's what I'm supposed to do, right? And I have to do the same thing for the rest of the partitions, which is from 35 to 60, right? And we're gonna change this guy to 35 to 60. Boom. And then we're gonna do the same thing from 60 to 80. Da, da, da. 60 to 80. Boom. And then finally 100. 80 to 100. 80 to 100. Nice. Now these are partition are attached. But remember, guys, this table is empty. It doesn't have anything. It's empty. So now, if I describe any of the tables, obviously G80, 100, they say a partition of grades parts for values from 80, and it will describe details of this. But there are no indexes in this table, nor on the grade. Let's clear this up. Grade parts. There are no index here. So now, here's what I'm going to do. I am going to insert into grades parts, select star from grades org. So what will this do? It will essentially copy the entire table into this table, right? But it will insert one row by row. And here's the beautiful part, guys. The beautiful part on this is every time you insert a row in this table, the database will decide which partition that row goes to based on the value of G. If G is 20, 20 is between 0 and 35, so it goes to G0035, and so on. So it's gonna distribute our beautiful table just like that. So let's see, what did I do? Oh, that's wrong. Just a different syntax. So let's do it again. Boom, boom. I keep doing this clear. That's just weird. All right, so this, hit it. And let's just wait for it. So it's gonna insert 10 million rows into this grades table. Nice, done. That's pretty fast, right? So now, guys, if I do select count star from grades parts, that's the same number. It's like 10 million and one, right? That's extra one. But if I do select max ID, not ID, G, the grade from grades parts, obviously it's going to be whatever. 99 is the max ID. However, if I go to the tables now, themselves, they are populated. But look at this. The maximum value is 0035 is actually 34, right? So let's do select count so you can see. Count star from G 0035. This is my first partition. There are only this much rows. Around how much is this? 3 million? Is this 3 million? Yeah, 3 million rows, right? And if I go to 35, 60, we have around 2 million and so on. It's just a random distribution. So if I do select max G from G3560, what do you think the number will be? I bet 59. Exactly. Because that's the largest grade we can get in this table. And so on. They are just distributed. So now, guys, still, my tables don't have an index, right? And that was by purpose. So let's go ahead and create an index. And should I create an index on all of the partitions? Well, prior to Postgres, I believe 11, that was the only way to do it. In Postgres 12, I believe, they added the ability, or 11 and above, you only have to create it on the partition table, grade parts, create index, let's call it grade parts index, right? Index on grades parts on G. The act of creating it on the master or on the leader partition tabled, it will create the same index on all the partitions, which is very, very powerful. Let's check this out. So it's gonna create that. Obviously, there is no index on the master table because it's empty. There's nothing. It's just a virtual table almost, right? So if I do grades parts, there is an index. It says, hey, this is your index. But if I go to G0035, hey, where does this index come from? I didn't create that. The database did for me, which is beautiful. If I go to 35, G35, 60, we have indexes on all of them. Beautiful. So now if I do explain analyze, select count star from grades parts where G equal 30. So now which table is gonna, where are we gonna hit, guys? We should hit the first partition, right? Let's check this out. So we says, hey, index scan only on which partition? G003G index on this partition. So we only hit one partition, right? And took us 1 second to query. Still, yeah, this is not much compared to what? To the original table, right? The original table, you're gonna see, guys, it's the same thing. Hussein, you say that partition are great and we're gonna be faster. Not really. If you think about it, my Mac here is at what, 16 RAM, 16 GB of RAM. And the Docker container doesn't have a limit, I believe. I didn't have a limit. So it's going to use all the memory it needs. And that is the same identical queries. There is no bounding limit. There's no memory bound. There's no IO bound. If I limited the container to like a 500 megs, right? And the index was so large such that it doesn't fit in memory, then you're going to start seeing the difference hitting the huge index versus hitting the smaller index, guys. But now you don't see it, guys. So guys, how about we show you the sizes of these indexes now compared to what we have here. So hopefully I remember the query. Select relational. All right, so the function called PG relation size, that's a function that gives you the size of the relation, and that's an index or table or anything. It's gonna OID, that's an object ID. And then I'm going to also select the relation name. And from PG class, that's the table, order by exactly the same thing. Relation size OID descending, because I want the biggest ones first. All right. So you can see, guys, this is our original table, grades original. And it's around what? That's around... That's bytes, right? So you divide it by 10,000, 100,000. So you get this in megabyte. So around 362 megabyte, which is not big, right? But multiply that, for instead of 10 million, make it 100 million, 500 million. Then you can start see this is increased. And these are the other partition. That's the oh my God. This is the rest of my partitions. Partition 1, partition 2, all the partitions. And these are the sizes. Still not something... that large. This is also 126 megabyte. That's apparently this is 0 to 35 is very popular grade. That's bad. Everybody's failing. So the original index is around what, 69 megabyte. That's the big large index, 69 megabytes. Guys, 69 megabytes is nothing for my Mac. That's why we didn't see a difference. But increase the size of the rows will increase the number of the index, and that will slow things down even more. So, but look at this, guys. The individual indexes are way smaller than the large indexes. So the individual index, which is the 035, right? That's the first partition, is around only 24 megabytes. So it's like what? 3 times smaller. And obviously querying this index is way faster than querying this index, right? The size and the index matter, where is it list, and then the scatter indexes and all that stuff, guys. So it really, really, really matter, guys, this little bit of information. And then the final thing I'm going to show here is there's a feature in Postgres. I want you to make sure that it's on. And it's called, let me get it right here. It's called enable partition pruning, right? Let's see what's the value of that. Enable partition pruning. The value of whenever partitioning pruning is on, and you want this on, guys, by default. If it's off, well, how about I show you what happened if this is off? All right. So let's set this to off. If this is off and I do explain, analyze, we don't really need to analyze, just explain. Select count star from grades parts, the partition table, where G equal 30. So which partition this is supposed to hit partition 1. But nope. Look at this stuff. It hit partition 1, it hit partition 2, it hit partition 3, and it hit partition 4. And I have no idea why do we have this option to begin with. Maybe it's like a safeguard somewhere in Postgres, but this is dangerous. So if this is off, you just wasted. This is the whole partition is useless because you hit all the 4 indexes, all the 4 partitions. Compare this to set it to on, execute the same query again, and look at this, we only hit 1 partition. So make sure that this thing, that partition pruning, is always enabled. Otherwise, you will not take advantage of this thing, guys. So what is the pros and cons of partitioning? Is this thing perfect? Obviously, nothing is perfect. There's always, everything is a double-edged sword when it comes to backend engineering. And we need to understand this thing as backend engineers, right? So the pros of partitioning is beautiful because it improves the query performance. Yeah, we didn't really notice as much of my demo because I'm using a laptop and I want a Docker container, but increase the size of the tables to the billions and make so that your memory bound or IO bound, because I wasn't either memory bound or IO bound in my table in my case, right? Because I had like lots of memory to work with. But if you are limited with the memory, you're gonna start seeing it because you're gonna pay to disk and you're gonna hit IOs and you're gonna start feeling the query versus working with a huge table, right? So query performance when working with a single partition or a little bit fewer partitions, it's a little bit way better actually than working with a huge single table, right? So working with a smaller partition is always better. So as long as I know how to hit that partition, that's the key here, right? So sometimes the database decide on a sequential scan versus a scattered index scan. So guys, the database always makes decisions. This is called a planner, right? The planner in the database says, okay, you're sending me a query and there's an index on the table, but I don't have to use the index. If you're gonna pull every single rows in the table, it's a waste to hit the index actually, because going to the index, you're gonna start jumping through an index and going back to the table and going back to the index and then go back to the table. That's actually slower sometimes to hit the index, right? And it's called scatter index scan. That's slower. So eventually the database decide to hit a sequential scan on the table directly. It says, you know what? It's not worth it to use the index for that particular query because I'm gonna select lots of rows. And that's a complicated logic, fuzzy logic by the database. It includes a lot of AI if you think about it as well to actually decide what to do. So based on that, a partition, giving the partition is actually smaller, right? Now it actually can make this decision easier because hey, sequential scan is actually better in this case than a scatter index scan on a huge table. So deciding which one is, you just made the life of database easier using partitions. Beautiful, beautiful. Easy bulk loading. So if you have, you can essentially just create a table and attach it to the partition immediately, right? To the partition table without worrying about anything. So you can bulk data load into a given table and then attach that table to an existing partition table, given that it actually the constraint and the checks are all valid and all that stuff, right? You cannot just attach an invalid partition, right? So this is a very popular thing, especially in MySQL. You can actually have a CSV file and create the storage engine, because that's only available in MySQL and MariaDB, I believe. Have the CSV be the storage engine for a given table, and Just like that, you have a table magically. If you have like a 300 million CSVs, you point your table to that CSV and you have a table that you can query immediately, right? And then you can use that to attach it. It's a little bit complicated, but that's one benefit of using MySQL over Postgres, for example. Obviously, that doesn't mean MySQL is better than Postgres. That's just one use case. Archive all data that are barely accessed into cheap storage, right? 2001 data. That partition is no longer used, barely queried, and you can check this thing real quick. That's actually pretty neat, right? This partition table is barely queried. So let's throw it in a table space so that nobody is using on a D drive that is pointing to an old hard disk that is slow and cheap, right? And let's use this our precious SSD in beautiful, our fast, frequently accessed data. All right, cons. Is this thing perfect? No, sir. Nothing is perfect. So what is the bad thing about partitioning? Updates that move rows from one partition to another are actually slow. So now, updating rows are no longer straightforward thing, guys. Think about it. In a huge table, if you update a row, you go to that row and just update it. End of story. But what happens if you update a row in a partition, and the act of updating that row moves the row from this partition to another partition? Let's say customer ID is a bad idea, but let's say grades. That's the example we gave, right? The grades, I moved the grade from partition was like partition 1 and I update the grade to 60. Now you just move the entire row from one partition to another, and that is slow. The act of update is now you're deleting and inserting into another table. That could be very, very slow. So you do this so many times. If you're moving one partition to another, you can actually harm your SSD. You can because especially you're jumping from one partition to another. So that is the SSD pages. If you're doing this so many times, man, that could hurt, right? So avoid updates that move rows from one partition to another partition. That actually changes the definition of what a partition is. Inefficient queries could accidentally scan all partitions. So yeah, if your queries actually include a where clause that knows that lets the database know which partition to hit, everything is rosy. However, if your query actually is inefficient, you will end up scanning all the partitions, and this might actually result in a slower performance than just having a single table, right? So let's say you say select star from this table where ID is greater than 1. you just basically selected everything. But instead of selecting one table, now you're selecting 7 or 5 tables based on how many partitions. So the database is jumping between one table and another. So that could be slow. So think about all that stuff, guys. Schema changes are challenging. DBMS usually manage that, right? So like if you update an index on the master table or the partition table, all the partitioned child tables will get that index. We saw that, right, in the demo. However, sometimes this doesn't always work. The database actually has to support this feature. So that's the interesting part, guys. Summary. Let's jump into it. Finally, that was fun. That was fun, guys. So we discussed what is partitioning. It's a very, very interesting feature, right? It's not always perfect. You have to know when to use it, I guess. Horizontal partition versus vertical partitioning. Literally splitting in horizontally versus splitting vertically and move the whole thing, right? Partitioning type. We talked about ranges, IDs, hashes. Partitioning versus sharding. Yeah, this is you want to use this before this. This is an overkill. Think about it, right? But yeah, sharding sometimes is beautiful. If you can find a software that hides the complexity of sharding, definitely use sharding. But not all databases support that. There are no software available that does sharding by default. I think Proxy SQL, Vitesse is another one. I'm not sure about others. And we decided the pros and cons, guys. Guys, what do you think about this technology? Let me know. And I'm going to see you on the next one. You guys stay awesome. Goodbye. Hey guys, some of you asked a fantastic question regarding the partitions topic that I made on my Introduction to Database Engineering course. And the question was, hey Hussein, I have a big table full customers and I want to partition by ID. How do I dynamically horizontally partition those if I'm going to create so many partitions? Can you show us a way to automate that? So I wrote you guys a script in order to do the partitions in an automatic fashion without you actually manually typing that, because it gets really tedious. How about we jump into it? So what we have here is a customer table, and let's say I'm going to support 1 billion customers. The default integer field in the ID can support up to 4 billion, which is 2 to the power 32. But for simplicity's reason, let's say just it's a billion. A billion customers is a lot of users, obviously. This is like it's a seventh of the world population. All right, so what we want to do is we want to create multiple partitions, and each partition we're going to have, let's say, 10 million each. Okay, and as a result, we will end up with how many partitions? If you do the math, it's 100 partitions. How about we go to the code, show you how to do it? I wrote it in JavaScript, but you can do it in any other languages. You can do it all, even in PLSQL. But I didn't want to introduce you like with a new language that we don't have to learn. So I'm gonna do it in JavaScript. It's with Node.js, so it's a very readable, so to the point, and you get to write client-side code, which is like, it's gonna become your backend in this case. How about we jump into it? So in this script, guys, I'm gonna share with you guys, I have already spun up a Docker container, and I showed you many times how to do that. It's very easy. It's just a one line of code, literally. Just let's write it out here so you guys can have it in case I'm gonna share this script. So all you have to do is just when you have a Docker, run dash dash name pg, give it a name, and then do dash e postgres underscore password, and then equal, this is equal the password, that's the password, and then expose the port 5432 because we're gonna need to connect to it, right? And what else? Finally, do detach and then Postgres. That will just show you immediately. So I don't really include the detach unless I make sure that my syntaxes are correct. But never mind. Never mind. So we have now a Docker container. You can just spin it up, and now we have it exposed to the your local machine. Now you can use this script to connect to that, right? My machine name, just change your host name instead of Hossein Mac to yours, and voila, you should be able to access that stuff. So here's the script. I have this Node.js will have two scripts: populate customers and create partitions. Create partition will first connect to the Postgres database, right? So which already exists, and the password of the Postgres using the credential of the Postgres users as we created right here. And then we'll connect to the Postgres database through the client. It's gonna create a new database, and if it not exists, it's gonna drop it. So be careful not to hit this script against an existing database that has a customer table. This is very dangerous stuff, right? So, no matter of fact, let's just comment that so you guys don't accidentally uh, run this against a real live database. I just added it so if you want to run it multiple times, right? Uncomment this code if you want to do that. Then the next step is to create the database customers. And then once we have the database customer, we no longer need the connection. We can close it actually. We now go and connect to the customer's database, right? That we just created. Gonna connect to it, and then we're gonna create a table, right? And this table is gonna be called customers. It has two fields for simplicity, ID and name, and it's going to be partitioned by range, which I explained in the partitioning course. We're going to execute that, right? But now this is not enough. We need to create the actual partitions, right? So if we did the math, we are assuming that we have 1 billion customers, right? And each customer, each table, each partition should have 10 million. So I did a little bit of a quick loop here to create 100 partitions, and each is going to have 1 million, 10 million rows, right? So I created two variables here, I times 10 million, right? So if the first loop was, this is going to be 0, and the second this is gonna be 10 million, right? Because I plus 1, 0 plus 1 times m. And then you can apply these loops. This is very simple programming, nothing fancy, right? Really here. And then the partition name is gonna be called customers underscore ID from and ID2. So that's the customer, that's the partition name, right? So every loop you're gonna be looping through each of them, and then creating all this stuff. So now we're gonna actually create the table that's called partition name that I just named here, and then we're gonna make it exactly look like the customers in terms of indexing, in terms of the tables. And you can just play with this, really add more fields, and then this code doesn't change because we're gonna like really inherit from the table structure. And then that's the beauty. That's what we need. We need to attach the partition that we just created to the customers table, and this is the range, right? The range is from this and to. And just pay attention to the to is actually -1. So if it's like up until 10 million, from 0 to 10 million, that means it's from 0 to 99,999,999. That's just that's something I learned the hard way. Okay, and then that's it. It's gonna do the second loop, execute the two queries because these are the first query, this is the second query. These are just strings, right? Now we're gonna actually create the partition, and then finally we're gonna close the data. How about we actually run this so you guys can see? To run this, very simple stuff. Once you clone your you can clone this repo. You have this code. Just do npm install, right? Which I already did to install the PG library, which will allow you to connect to Postgres, and then do this. Zoom in so you guys can see. A node index, not index, called create partitions.mjs. That's it. Once you do that, oh, we have an error. I think because I'm already connected to the database. Let's go ahead and exit here. All right, and let's run it again. I'll need to comment this out because I already have the database Postgres. That is good. All right, so now we're gonna drop, and as you can see, look at that. It's creating all these beautiful partitions, and that's it. We're done, guys. And we're gonna, before we push it, let's just comment this out for you, and that's it. Now you will need to populate this thing, right? And it's very simple. As you start inserting customers, you only need to target the customers table. That's it. And the database will do its magic. Based on the ID, it will try to insert to the right database. So I wrote here a small script that creates 10 million customers in one shot, right? In a loop. So again, for 100 times, we're going to do this 100 times. Let's do this again. Node populate. Whoop. Customers. All of a sudden, that's it. We're just inserting those customers. And that's it. I'm not going to go through all of them and wait because that's going to take a long time to complete, but I'm just going to wait for maybe a one or two. And meanwhile, while this runs, let's go ahead and show you how to connect to the actual database. All right. This is how, but let's do it again. So docker execute -it pg part, that's my container name. psql -u, the user is Postgres, and the database -d is customers, right? Boom, and just like that, you're in the database. Now you can do like a select max ID from customers table, and tells you what is the maximum ID, so we can show you the customers and all that stuff. Like, all right, so it looks like we have inserted 10 million customers. Now let's describe this table that we just created. If you do customers, you can see that we have an ID, we have the name, and we also have a partition range ID, and it says I have 100 partitions, but it's not going to show you because there's a lot of partitions. You can use /d plus to show all of the partitions. So all -d plus customers. And that's it. It's going to show you all the beautiful partitions. And you can just start querying all of them. So let's query the first one. These are just normal tables at this point, right? We can do select, I don't know, count star from, boom. And it's going to query this table normally, like just another. And you can see that's the number I told you about. All right, guys, that was a quick video showing you how to automate this stuff. I'm gonna share this code with you guys. I'm gonna see you in the next one. You guys stay awesome. Goodbye.